Forces. Let's start with weight, which is due to the force of gravity. Close to the surface of the Earth, where the gravitational force is nearly constant, we can calculate weight as the force of gravity equals mg, and notice we're showing force of gravity as a vector, and also the acceleration due to gravity as a vector, because it does have direction, it's pointed down. Or if we just want to find the magnitude, we call that weight, and weight will just be equal to mg. G is a vector, and near the surface of the Earth it is 9.8 meters per second squared. And typically in these problems we're just working with the magnitude, and the magnitude of G we'll just denote as G. Notice we've got the vector form in bold and the scalar form in unbold. And W, weight, is equal to mg. Anytime a force is exerted on an object, that force is caused by another object. So in other words, you need two objects involved to have a force. Newton's third law states that whenever one object exerts a force on a second object, like the cat exerting a force on the table in that direction, that's this vector here, then the second object exerts an equal force in the opposite direction on the first object. So the cat's exerting a force on the table, and the table is exerting an equal magnitude force on the cat in the opposite direction. Whenever one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first object. In the previous example of the cat and table, the force that the table exerts on the cat is the normal force. Another way to state Newton's third law: for every action there's an equal opposite reaction. Now here's the key. These forces or actions are always applied to two different objects. The forces are exerted on different objects. Why do we have to say that? Well, if we assumed that both forces are acting on the same object, they would add up to zero and nothing would ever move. So in this case here, the person here is exerting a force on the floor with his hands, and the floor is pushing back with an equal force on his hands. So that will enable him to move because there's only one force acting on him. But if you just added these two up, it would be impossible to ever do a push-up because you would just say, hey, the forces cancel out, they equal zero. But that's not true. Only the force on the hands will move the athlete in the upward direction, and the other one is the force pushing down on the floor. An object at rest must have no force on it. Well, that's because Newton's second law: if you're at rest, your acceleration is equal to zero, so the net force must be zero. So if the object's sitting on a table, you still have the force of gravity, and that's pulling the object down, and we call that the weight of the object, W equals mg, or of course we can just call it the force of gravity. But additionally, what other force is there? And you can go back a couple slides and maybe probably come up with the answer. The other force is called the normal force. That's the force exerted perpendicular to a surface. And you can see over here, we've got gravity pulling it down, and the force opposing that would be the normal force on the table. Both of these forces are acting on the object there, that vase, and they cancel out to be zero, which means the vase won't move. Now the normal force is exactly as large as needed to balance the force from the object. So if I put a heavier vase here, the normal force will increase. If I just put a little pebble here, the normal force will decrease. However, if the required normal force is too big, for example, if I put a 2-ton block here, something breaks. The table will break. The table cannot generate enough normal force to hold up a 2-ton block. So, the words normal and perpendicular are synonyms. They mean the same thing. And perhaps you saw that in your math class. Normal and perpendicular. Friction. There are many types of forces that occur in nature. Perhaps none is more familiar to us than the force of friction. And we call that F, and then let's just call it Fr for friction. Friction is a resistive force that opposes the motion of an object. So if an object is moving this way, the force of friction is in the opposite direction. Friction is the reason objects stop rolling or sliding along a surface. It is the reason it is difficult to start pushing a heavy box along the floor. We have many different kinds of friction. Frictions between solid objects and air is called air resistance. Friction between two fluids is called viscosity. Where does friction come from? On a microscopic scale, and that's what we're simulating here. We have this little high-powered microscope looking at the interface between this block moving at a velocity v and a surface. All surfaces are rough on that scale. This leads to very complex interactions between them that we don't have to worry about yet, but we can model the force in a simple way. Friction that acts on an object that is already in motion is called kinetic friction. For kinetic or sliding friction, our equation is the force of friction is mu k times Fn. So what are those terms over there? Well, we've already talked about the force of friction. Now, mu k is the coefficient of kinetic friction. It's a number, that's all. And it's different for every pair of surfaces. F sub n is the normal force, which on flat, non-accelerating surfaces is equal to the weight of the object. So if I have an object here, it has a certain weight, and let's say it's sitting on a table or something, the normal force will be in the opposite direction and exactly equals mg. There are tables that tell you what the kinetic friction force is. A larger coefficient of friction means a greater frictional force. Also, the coefficient of kinetic friction depends on the surfaces involved. So let's start with the top. Wood on wood has a 0.2, and notice all of these are below 1. Ice on ice, much lower. There's much less friction for ice moving on ice. And what's really cool is one of the lowest values, at least for this table, are the human joints and limbs, which is why they last so long. Even better than Teflon on Teflon. So the higher the value of the coefficient of friction, the higher friction there is between the surfaces. And notice it even depends what's going on with the surface. So rubber on dry concrete has a higher coefficient of friction than rubber on wet concrete. Whenever we want to solve problems involving forces, we need to keep track of the forces acting on your object. So here we have a cat, and we want to find all the forces on the cat. The way to do that is with a free body diagram. We'll start with a dot representing the object. We don't have to learn how to draw cats. And then draw arrows coming out of the dot for each force acting on the object. So for the cat here, we have the normal force going up and mg going down. And we're going to write it with mg, not w. Because when you do these equations, perhaps we can get m to cancel out with other variables. Let's just make it a little more involved, and we're going to pull a block with a rope across a rough surface. Right there. And we don't have to draw the block, we just draw the dot here for the block, and we have mg and normal, like we just talked about on the previous slide. And then here is a force, we're going to call it a tension force. When you have a rope pulling something, that's a tension force. And then going the other way, we have the force of friction. Now, if the block is accelerating, the tension force will be greater than the friction force. So when you add the two of them together, you'll get a net force in that direction. But if the block were not accelerating, if it was moving at a constant speed or not moving at all, then the tension force and friction force would be equal in length. This way there'd be no net force in the x direction and no acceleration.